just showed that John's lemma, using that we could prove the well-ordering theorem. Let's take a look what we did. What was the well-ordering theorem? We said that every set can be well-ordered. If you given any set X, there is a partial order on that, with respect to which it becomes a well-ordered set. Okay. The line of thinking was the proof was the following. So what did we do? Let X be any set. I'll just recollect the proof. Then what we did was, the first step, we looked at all well-ordered sets whose base sets were subsets of X. So Wx, collection of all well-ordered sets, base set, I started early, base set X. Then we introduced a partial order on Wx. We call this the continuation. Okay. This partial order was called the continuation. It was essentially some idea of concatenation. Okay. W1 is W2 is a continuation of W1 if W1 goes and sits as a suffix of W2. Okay. That's essentially the idea. Then we showed that the partially ordered set Wx satisfies the hypothesis of Zorn's lemma. What is the hypothesis of Zorn's lemma? Every chain must have an upper bound. We showed.
Continuation that you said. The definition says it's enough if there is just one element which sits beyond all elements.
There is one element which comes as the first element after W1.
Correct.
It is the first element in W2 minus W1.
That is not told in the
But you look at the definition again, okay? Carefully. When you get the notes, you look at the definition. The hypothesis of okay. So therefore, essentially this idea, okay, you now look at it and write your own proof. The partially ordered set satisfies Zorn's lemma. Therefore, there exists a maximal element in Wx. Call this maximal element as W. That maximal element will be a well-ordered set because every element here is a well-ordered set. So the maximal element must be a well-ordered set. So it should be a well-ordered set with the base set being a subset of X. If we show that it is exactly equal to X, we are done. Already we are, that's exact. So next claim, show X, and we are done. So that's the line of argument of this. Right. So we have so far seen. If you look at the well-ordered set, the well-ordering theorem, essentially, eventually it boils down to getting some maximal element in a partially ordered set. Once you catch hold of that, and that's the end of the story, you just assert that that is indeed X. Okay. So all these theorems, the one we had Tukey's lemma, then we had the Zorn's lemma, and then we had this well-ordering theorem. All are in a sense, all are asserting the existence of some kind maximal element in some types of partially ordered sets. And we got this Zorn's lemma gave us the well ordering. Now I am going to look at a consequence of Tukey's lemma. Now, what is Tukey's lemma? Recall, we have a family F, a family of sets with finite character. Then F as a maximal. Then F as a maximal. This is Tukey's lemma. Now, of course, family is not trivial. What if you are looking for an element? So let's say non-empty family of non-void family of finite character. So now I am going to use this Tukey's lemma to get at something else. Suppose we start with any partially ordered set. And of course, we are always looking at non-trivial. There is some element in trivial. So there may be several chains in P. One chain is the empty chain. The other chain is you take a singleton element and form a chain out of it. The singleton element chain having only one element. Okay. So phi and for any x in P, this set x are all chains. Okay. See, this is a clever thing. See, what does the chain require? If there are two elements, they are comparable. Don't have two elements at all. Question doesn't arise. Only one element, and it's comparable. So, all the singles, so there are chains. There may be more. There may be chains with two elements. There may be chains with infinite number of elements, and so on. Who knows? But we are guaranteed there are several chains. Okay. So now let's collect all the chains in a basket. So let's see with the collection of all chains. Let's see with the collection of all chains in that partially ordered set. Now, what is a chain? After all, it's a subset of P. The chain is a subset of P. So, each chain is a subset of P. So, this is a collection of subsets of P. Okay. And what subsets? Special types of subsets. Those subsets which form a chain. Now, whenever you have a collection of sets, you can always put the inclusion relation and make it a partial ordered set. Okay. So C is a partially ordered set. Every time you have a collection of sets, one of the natural partial order is the inclusion relation. So that's a partially ordered set. Now claim C is a finite character. Call it as star. Suppose this is true, what happens? Tukey's lemma says there is a maximal element. What does it mean to say a maximal element of this? Every element is a chain. That means there is a maximal chain. There is a chain which cannot be expanded any further. Okay? Then by star we get and Tukey's lemma. That there exists a maximal element C0. That is, there exists a maximal chain any element of this is a chain in that, and it's maximal in the sense that it cannot be expanded any further. So this is what is known as this This result is known as the Hausdorff maximality principle. Write that. Every non-empty poset has a maximal chain. Every non-empty poset has a maximal chain. Because this is modulo star. You have to still show that the collection of chains is a finite character. Now, is it difficult? If you have a chain, any finite subset is also a chain. So essentially that's what it is. So easy. Okay, I'll just write it here. Easy because every finite suppose there is a chain. You want to show that if C belongs to C, every finite subset of that belongs to that. But that follows because every finite subset of a chain is a chain. Okay, that's obvious. So this is what is known as Hausdorff's maximality principle. Every non-empty partially ordered set must have a maximal chain. That is, you have a chain which cannot be put as a proper subset of any other chain. That's the end of it. So what we have got now is one more result. Okay, let me write it here. So what we have is Tukey's lemma. We have now Hausdorff's maximality principle, and we had Zorn's lemma, and then well-ordering theorem. With these two, right? Now you will see that the HMP gives rise to Zorn's. We can give a proof of Zorn's lemma if we guarantee HMP. If we have HMP. So what we are going to show therefore is the Hausdorff's maximality principle. Using that we can prove Zorn's lemma, and therefore essentially what happens is if we have Tukey's lemma, this is a theorem, this is a theorem, this is a theorem. All these follow from Tukey's lemma. So now I am going to look at first we have the duster, then the cloth, again the duster. It's a well ordered. So, we next prove. Let me put the order of what we will do. First of all, let's not get into proof because that's it. We next prove that HMP implies. What does Zorn's lemma say? If every chain has an upper bound, then it must have a maximal element. Right? That's what it says. In particular, the HMP says there will be a maximal chain. So that maximal chain must have an upper bound. So catch hold of that upper bound for the maximal chain and claim that upper bound will be a maximal element. Okay, it's a line of thinking. So let P be any partially ordered set, but always it's a non-trivial partially ordered set. Okay. Then by HMP, there is a maximal chain. Call it E. Because the Hausdorff's maximality principle says that there will be a maximal chain. But the hypothesis of Zorn's lemma says every chain has an upper bound. Therefore, by the hypothesis of Zorn's lemma, this maximal chain will have an upper bound. So, why the hypothesis? Vittal, this maximal chain C naught has an upper bound, what do you call U naught? Is an upper bound? Claim U naught is a maximal element. U. That's the proof of Zorn's lemma. Zorn's lemma says if that hypothesis is there, there must be a maximal element. We have produced it. Okay, proving. That hypothesis of Zorn's lemma implies inclusion. That's what we get. If U naught is the maximal element, then you give me the fact that every chain is bounded, automatically I will conclude that there is a maximal element. So modulo, there is always this one fact that will have to be crucially very correct. Now, okay, let me complete that also. So how do we show that? That's a suppose that's not a maximal element. What would that mean? So somebody will be going to his right. What is meant by maximal element? Nobody can go to his right. So if he is not a maximal element, somebody will go to his right. If somebody goes to his right, append him to C naught. That will still be a chain. That will violate the maximality of C naught. Okay. If U naught is not a maximal element, there exists an X in P such that U naught is strictly less than X. Somebody will go, somebody different will go to the right of U naught. Then C naught union X is a chain. Why is it a chain? We want to show that any two are comparable. Any two and C naught are comparable. So the only problem will come from one fellow and one fellow here. But every fellow here is smaller than U naught and therefore smaller than X. So therefore they are also comparable. So any two fellows in this are comparable. So therefore violating that C naught is a maximal chain. Okay. C naught was a maximal chain and it cannot be blown up any further. So therefore that, so QED. So U naught is a maximal element, assume we get a constant. So we have a very nice chain of theorems, we can call them, namely the following chain. So let me keep this chain now. Tukey's lemma implies Hausdorff's maximality principle, implies Zorn's lemma, implies well-ordering theorem. Finally we will put a full cycle. Okay. Alright, so now I come to a very brief discussion of the axiom of choice. Okay, so let's start with some very simple things. Suppose I have two non-empty sets. Suppose I have just two non-empty sets. Let's understand this context of two. Then, suppose f is a function. So we'll write this as a finite collection of sets where alpha belongs to the index set. What is the index set now? This one 2. It's a very complex way of writing it. Okay. In anticipation of how complex we are going to make it. So this is the collection of non-empty collection of non-empty sets. Each set is non-empty and the collection is non-empty. There are sets. Now suppose f is a function from this index set to the union. Such that fj, f alpha belongs to A alpha, whatever is alpha. Okay? That means f of 1 must go to A1 and f of 2 must go to A2. That is, f of 1 belongs to A1 and f of 2 belongs to A2. So this is like this, A1 and A2 are two collection of people. Okay, we are trying to get representatives for these two collections. Okay? We are trying to choose people representing these two sets. So, such a function is called a choice function. The choice function is one who picks one representative from a collection of sets, and it's not even big. So now look at f1, f2 for such a choice function. It's an ordered pair. Where does it belong? f1 is A1, f2 is in A2. So this belongs to A1 cross A2, the Cartesian product. This belongs to A1 cross the Cartesian product of A1 and A2. So what we are saying is, if we have a choice function, it automatically can be identified with an element of the Cartesian product of A1 and A2. So every choice function can be identified with an element of A1. Conversely, if we have an element A1, A2 in the Cartesian product, we automatically get a choice function. We get a choice function defined as f1 must go to A1, so that's this choice, and f2 must go to. So what this boils down to is the elements of the Cartesian product are simply a different avatars of this choice function. That's all. They just appear in a disguised way. The elements of the Cartesian product are disguised or coded versions in the modern language, the coded versions of the choice function. Or choice functions are coded as Cartesian product, or Cartesian products can be coded as choice functions. Okay. So therefore, we can interpret the collection of all choice functions as the Cartesian product of all such choice functions, and the Cartesian product of A1. Now, this we take as the definition of the Cartesian product when we have an arbitrary collection. Okay, suppose you have A1, A2, A3, well, still we know what, at least intuitively you have the idea of Cartesian product. Suppose you have a sequence of sets, still we have. Suppose we have an uncountably infinite collection of sets. Then what is meant by the Cartesian product? We can't say A1, A2, A3, etc. where A1 belongs to A1, A2, because there is a problem there, it's not a sequence. So therefore, we have to interpret the Cartesian product of an arbitrary collection in terms of the choice functions. Okay. So we generalize this to get the following definition. Definition, the let A alpha belong to I be a non-empty collection. What does that mean? The index at I is non-empty. Non-empty collection of non-empty sets. What does this mean? The sets are non-empty. A alpha are not 5 for every alpha n. So we have a non-empty collection of non-empty sets. Then the Cartesian product of this collection is denoted by, well, whenever we have a product we use pi or some notation. So since it is a Cartesian product, we denote this the product over all the indices. This is defined as all the choice functions, the collection of all choice functions f mapping the index set to the union of these A alphas such that f alpha belongs to A alpha for every. That is how we define the Cartesian product. Okay? So what we are doing when we have a finite collection of sets, we are writing the choice value as the coordinates, that's all. The choice for the first, who is the representative of the first set, you call him the first coordinate. Who is the representative of the second set, you call him the second coordinate, and so on and so forth. So here also you can call f alpha as the alpha coordinate of this Cartesian product. Okay? So f alpha you can call it as alpha coordinate. Now you already see something happening here, namely if you had a finite number and you can put f1, f2, f3, f4. If you have a sequence, I could put f1, f2, f3, f4. You are looking for some order there in which you have to put these coordinates. Then we are done. Okay, so when you had an arbitrary collection, if really we had a well ordering, we could still have thought of defining them in terms of that well. That's essentially what we are going to see eventually. Okay. So, but unfortunately, stated in this way, it could not be shown that this Cartesian product will be non-empty. There is no way. This looks like a very tricky situation. When you look at these situations, it looks very obvious. But we are not an arbitrary collection like this, we are talking in terms of such a function. We don't know whether such a function exists. So the attempt to prove that there will be such a function using the other axioms, theorems, etc. of set theory totally failed. And eventually perhaps out of sheer exhaustion, that is exhausting all attempts, and also physical exhaustion and mental exhaustion, Zermelo said let's add it as an axiom. Okay? And that's what is called as the axiom of choice. Okay? It could not be proved from the other axioms of set theory, the Zermelo-Frankel system, which I once discussed. I mean, I didn't mention that's called the Zermelo-Frankel system. That the Cartesian product arbitrary, non-empty collection of non-empty sets is non-empty. Certainly it is not a it's not an empty statement, it's a non-empty statement. It's a lot of punching there. The collection is non-empty, the sets are non-empty, then the Cartesian product will also be non-empty. That is, could not prove there exists a choice function. So therefore, almost if somebody grumbles still that this is modern mathematics, let me remind you that it was about 102 years ago that Zermelo added this as an axiom in set theory. So in 1904, stated this axiom of choice. He added this axiom to the other axioms of set theory. That is, there exists a choice function for any arbitrary. From then on it is the same. For any arbitrary non-empty collection of non-empty sets, you add this part. Cut and paste. Okay?
So could not prove that does not exist a choice function.
What do you mean?
That is
could not prove there exists a choice function. Non-empty, the Cartesian product is non-empty means what? What are there in the Cartesian product? All choice function. We didn't know that even there exists one choice function. So this way they could not prove that there exists a choice function. And but given, well, incidentally, let me finish this question. But given Hausdorff's maximality principle, you can prove the axiom of choice.
For the countable collection,
Well, that is also axiom of choice. We say pick an element. What do you mean by pick an element? That picking, if you look at carefully from the axiom, there must be something that says that picking is possible. What that is where I think I wanted to quote. I controlled myself, but you have not forced me to quote. Zermelo said that what is appears to be self-evident should not be confused with what is provable. That is his quote. Okay, so it's self-evident. It looks like I have two classes. I can pick a representative. Okay, but that's okay physically. But taking the systematic axioms that are there in set theory, does that imply? And that was not possible. So suppose you are given the Hausdorff's maximality principle, then you can prove the axiom of choice. Okay, let's look at that. So I have this collection A alpha. What does Hausdorff's maximality principle say? Oh, I'm sorry. What is that? Well ordering theorem. We had this chain. Somewhere I had a chain of theorem. Where was that chain? It's gone. The chain has disappeared. Let me keep that chain now. Suki's lemma led to Hausdorff's maximality principle, led to Zahn's lemma, led to well-ordering theorem. Now I am going to show that axiom of choice, AOC. So this is the given non-empty collection of non-empty. I'll just indicate how the argument goes. Look at X, which is the union of all these fellows. Okay? Now by well-ordering theorem, any X can be well-ordered. So this can be well-ordered. Okay? So by WOT, well-ordered theorem, there exists an order such that this is a well-ordered set. Okay? Because well-ordered theorem says any set can be well-ordered, any non-empty set can be well-ordered. In particular, this can be well-ordered. If this can be well-ordered, now I will give you a choice function. A alpha is non-empty. That is part of our hypothesis, and it's a non-empty subset of X, and X is a well-ordered set. So it's a non-empty subset of this well-ordered set. What is the meaning of a well-ordered set? Every non-empty set must have a first element. So implies there exists, you see this is proof, there exists A alpha belonging to A alpha such that A alpha is the first element. The choice is over. For every A alpha, the choice is the first element of that set.
The non-emptiness itself doesn't guarantee.
Pardon me?
No, the non-emptiness of A alphas.
Yeah, that is what well-ordered theorem says. Every non-empty subset.
No, no. We want to pick an element from each of the A alphas. Right?
Yes, but I have to show that there is something that guarantees a picking is possible.
Here picking is possible.
Here, because the theorem says every well-ordered set, there exists the first element.
But a non-empty set also there exists some element.
There exists some element.
Yeah.
True.
But I can't pick it.
There is no guarantee. See, the problem is mental thinking is different from the logical deductive proof. That is why Dharma law is very careful. What is appears to be self-evident and trivial should not be confused with something that is provable from the axioms. Right? Okay. I mean, just as a matter of it's all philosophical discussion. Eventually, it boils down to philosophy. Okay? Right? And therefore, choose the choice function. There exists choice function. Yeah, mapping union A alpha, alpha belonging to I to this. Defined as F alpha, the first element. These uniquely pick the first element of A alpha. Okay, so what are we? We have completed this check, but it looks like we have proved axiom of choice. Then why did Zermelo add it? But unfortunately, it's all true provided Tukey's lemma is there. And Tukey's lemma was originally proved assuming the axiom of choice. Okay, so you go in one full circle. Okay, this is Tukey's proof. Okay. I am not going to go to this proof. This is also a little bit inward, but I think I'll skip that. Okay. So what happens is therefore it goes in a cycle. What it boils down to is all these are equal. I can remove axiom of choice from the axioms of set theory and put Tukey's lemma there as an axiom. Or I can remove it and put Hausdorff's maximality principle as an axiom. Then the other things are all theorems. Okay. Any one of them is an axiom, the others are all theorems. But what do you put as an axiom always is something which looks self-evident. Okay? And the axiom of choice looks self-evident. People buy it easily. So put it there. Okay? Hide up all the other things. If I had put Tukey's lemma as an axiom, where did he get this from? It looks like magic. But after all, he's asking for something which is not very great axiom of choice. Give him that. Then you sneak in all these theorems. But the interesting thing is there are lots of parallels in. Maybe I should spend time some comments again. There are lots of parallels to this in the history of mathematics. One of the greatest parallel is the parallel axiom. Okay, now we can relax and forget for the time being. See, one of the things that, if I remember correct, Euclid wrote his books around 350 BC, let's say around, maybe, don't say it was 347 and a half BC or something. Give or take 50 years, okay, it's 350 BC, right, okay. Then, almost up to 1800, for 2000 years, Euclid's book was like unquestionable truths in mathematics. Okay? Just facts. Everything has been logically and deductively proved. Nothing is questionable. All you have to do is master Euclid. There's nothing else that you can do better than that. And as I pointed out several, maybe a couple of times, this was also used as an argument by the religious groups that the pursuit of absolute truth is a worthwhile pursuit, and Euclid is the greatest example of this. He has gone to the absolute truths in mathematics, established. And one of the greatest, one of the good things about Euclid was that he tried to systematize mathematics, put certain things as axioms or postulates, and then started what are the conclusions we can make, and also the axioms and postulates you put them in a consistent manner. Okay, so that one did not contradict with each other. Okay. So they were consistent, and one of the axioms that he put, self-evident, as you say. Okay. Given a line L and a point P not on L, there exists, I'll underline, one and only one, there exists one and only one line through P and parallel to, that is, give me a line L, give me a point P not on L, there exists a line. In fact we all learn how to draw that line, there exists a line. He completely hoodwink people and believing that's true, it's so self-evident. Okay. Right, so there, this was one of the most debated axioms. Many people thought it must be easily provable from the other axioms. Several, almost, it's 2000 years, there's a total failure. Okay, it wasn't possible to prove this as a theorem, so it had to be accepted as an axiom only. So what happened in the beginning of the 19th century was a very serious questioning of this axiom. In a sense that you could have geometries in which this axiom is false. You could have geometries in which the parallel postulate is false. Now the parallel postulate can be denied in essentially two ways. One way is, you say there exists a parallel line. Deny the existence itself. Given a point, a line L and a point P, there does not exist any line passing through P parallel. Another way is, you say exists, but there are many which exist. The only one, the uniqueness of the parallel line, you can deny. So you can construct models of both these geometries. Now roughly, all this problem starts because Euclid doesn't define what is a point, what is a line. It's taken for granted. It's an undefined terminology. So all you have to do is define point. This is what Hilbert said. That you must do geometry in such a way. If you replace the term point by a donkey or a monkey and a line by a coffee or tea, and still replace all the terms, the axioms are true, the results must be true. So this is independent of what a point and what line you are talking about. And it turned out, for example, should I do? No, I don't want to get into non-Euclidean geometries. Tempted to, but I am not going to. What is a line? Point is something which cannot be defined. Okay. Any arbitrary collection of elements can be taken as points. And what should be a line? A line is something that is defined by 2 points. Okay. So then the story starts, the chain starts. Now let me just intuitively, don't quote me and then somebody from across behind this building, mathematics professor, you taught wrong projective geometry and things like that. But if you want to do right projective geometry anyway in the beginning you don't understand it. It is better to have an intuitive feeling first. So what I will do is, let us take intuitively our 3-dimensional space. I don't know why I started geometry. Why did I start geometry? Oh, I wanted to come to parallel. Let us take 3-dimensional space where we are living in. I will think of any line passing through the origin as a point. My new geometry. In a new geometry, every point is a line passing through the origin. So what does it mean? It's not great because every line is essentially denoted by certain numbers. Okay, the direction cosines. Right? So those really a point. I can take it as a point. Some numbers as a collection of triplet is a point. So therefore every line through the origin is going to be a point. And then 2 lines through the origin define a plane through the origin. So that means my line. So in my geometry, points are lines through the origin and lines are planes through the origin. Okay? Now you take any 2 lines. They are both planes through the origin. Any 2 planes passing through the origin intersect on a line through the origin. So there are no parallel lines. Every line intersects. So there is no question of parallel lines. So no matter where you go, you are not going to get a the existence of parallel lines is totally denied. Completely denied. That is, every pair of lines will intersect. And therefore there is no question of the complete existence of parallel lines in the entire geometry is denied by this. So this is rough. Yeah, I mean, again, this is only an intuitive idea. You have to go through all the formalisms required to put this, okay, into correct picture. Yes. What is?
The question is, what is the definition of parallel in the next new?
Intersection. Parallel means they don't intersect. They don't have a common point.
And the intersection should be a line. Line is a point.
2 lines must intersect. Yeah, any two planes passing through the origin intersect at the line through the origin. So the line through the origin is the point.
So, but in 3 dimensions there are these Q lines.
That's all I am going to discuss. I said, no, everything passes through the origin. My points are lines through the origin. My lines are planes through the origin. The rest of it is the ballgame. Okay, that is roughly the starting point. Now you have to formalize all these things. You have to somehow take a line through the origin to be a point on the sphere and then start bringing in the, now let me not get into the formal construction of the whole space and things like that. But intuitively this is how it is denied. Now there are lots of questions that should be asked, that was asked, and all these questions were answered by formalizing these constructions, and then you can give a formal construction of the correct non-Euclidean geometries where parallelism is denied totally. It is, if you look at it another way, you think of, in fact, Riemann almost ridiculed the very word of geometry used by Euclid in the sense, by his construction. Because after all, what does geometry mean? Measurement on the earth. But the surface of the earth is a sphere, roughly. Okay? So, what is meant by a line then on the sphere? We are talking about skew lines. I am in fact talking about parallel lines. Right? So, what should be a line? The shortest path between 2 points. And that's a great, that should be a part of a great circle. But any 2 great circles on the sphere meet. So, there are no parallel lines. This is another way of looking. These are all just very quick disposal. But you have to sit down and put these things very formally. Okay, the shortest distance is geodesic, what are geodesics on the surface of the sphere, prove that they are great circles, and prove that they need to great circles meet, etc., etc., etc. Because after all, what is a great circle? Plane through the origin. Again, it is the intersection of the sphere with the plane through the origin. That is where those planes through the origins can be formalized. Okay, there are lots of things that have to be done, but intuitively that is what it is. So, the creation of the non-Euclidean geometries in the beginning of the 19th century, 1800 plus, the that really, in a sense, that shook many foundations of thinking, in a sense, the very idea of thinking, but at the same time created newer ways of thinking. Okay, so that you could create several types of geometries. It is not the Euclidean geometry that alone says, and then subsequently, very nicely, the German group essentially really said that geometry is simply the study of invariants under the action of a group. Eventually, after the group theory was created and it was all over by the second half of the 19th century, essentially geometry became the study of invariants under the action of groups. Okay. And that way, the idea of geometry became so very big. Euclid was just one small piece somewhere sitting. In fact, somebody like Bertrand Russell, who never liked Euclid, would have said, perhaps somewhere, that Euclid was shown his place in this whole universe of geometries. He said in some corners, you are not the dominating geometry, you can say. Okay. So, in fact, one of the greatest critics of Euclid was Bertrand Russell. Was it Bertrand Russell? I think so. I get confused between Bertrand Russell and Plato. One of those two philosophers. I think it was Bertrand Russell, who clearly went on to the extent of saying that undue credit is given to Euclid for bringing in beautiful logic and deduction into the mathematical thinking. But this is all bogus. You should not give any credit, because most of Euclid's proofs depend on figures, and any proof which depends on figures is not believable. It must be proved abstractly without any picture, because you can always draw a picture and hoodwink you, which is convenient to you, and then say, look, it's there. Most graph theorists do that. Right. Okay. So the second maybe major crisis in mathematics was when the axiom of choice and the continuum hypothesis were thrown in, and they were not again provable from the axiom. So essentially, in both the cases, even in the geometry case, you said that you can have geometries in which the parallel postulate is true. You can have geometries in which the parallel postulate need not be true. You can have geometries without the parallel postulate, and you can have geometries with the parallel postulate. Both are meaningful geometries. In fact, if you look at I just said that the denial of total denial of parallelism is what one way of denial. Let us look at the other way of again, this is intuitive. Okay. It is not the formal way of doing it, but best thing is to look at the intuitive ways first and then look at all the formalisms later. Suppose you want to create a geometry where there are lots of parallels. Okay, so let's look at it this way. Suppose, just for the purpose of imagination, assume that Euclid was put in this room and he knew nothing else about the world, but he was still equally intelligent, his interest was in geometry. Then the only plane he would have seen is the board. Then what would he have stated? If I give you a line, for him the lines are extendable only as far as the board extends. That's all. Okay. What does it parallelism mean? As far as you extend, they don't meet. So given a line and a point P not on the line, you would have drawn many such parallels. Okay? So you would have replaced it axiom by given any line and a point P not on the line, there are many parallels which pass, infinite number of parallels which pass through that. So it's all very tricky situation, okay? So shrinking the plane to a finite situation creates a lot of problems. Not a lot of problems, creates newer ideas, okay? So there could be all kinds of geometries with the parallel postulate denied by the existence or denied by the uniqueness, or perhaps both. Okay. Well, you cannot deny both. There is non-existence, there cannot be many. Okay, whatever. So exactly the same way, in the axiom of choice and the continuum hypothesis, in both these situations, similar things arise. The axiom of choice is consistent with the other axioms of Zormelos and Frankel, and it was independent. Eventually, in 1963, Cohen showed that axiom of choice is independent axiom. Just like the parallel axiom was an independent axiom, you can have it or you need not have it, still the system is consistent. Similarly, you can have set theory with axiom of choice and set theory without an axiom of choice. In fact, you can do complete set theory without axiom of choice. The only problem will be you will have very few people maybe to even talk to. Okay? So because most people find it convenient to have the axiom of choice and work with it. It may require some just like some very powerful man like Riemann was needed to show that non-Euclidean geometries are more useful, or really very useful. Like that, somebody must have still yet to come to show that non-axiomatic set theory is more useful and more realistic than the axiomatics. We do not know. But right now, it's convenient to assume what is meant by convenient? Anything which seem to be true are true. That's all. Convenient assume. I think that way the work of Vittal and Cohen during that period was earth-shaking in the sense it brought back to memory people that there is something that there is a limit to which you can go. At every limit you cross, there is another limit that comes into the progress that you can make. And again, this sort of well-ordering you will have to do whether there is a maximal learning that is possible and things like that. So there is a lot of philosophical things that go on in this and they get merged.
So, but can all things be proved without axiom of choice?
What do you mean, can all things be proved? All theorems which are proved without using the axiom of choice can be proved. So you have to now see through. You have to see through all that has gone on in analysis and algebra and see, well, even if there may be some theorems which are proved using axiom of choice, whether I can prove them without axiom of choice. So that's why I said you'll have a very lonely life, but there are lots of papers you can write because nobody else is working on it. The only thing is you have to start your own journal. Many journal fellows, they want the referees to read that. And many fellows did like that. I remember, what is this guy who had this journal of rational mechanics and analysis? The mechanical engineer. Forget his name. He started a journal because his paper was rejected. He thought that he had some very original idea. He was right, of course. He had some very original idea, and the conservative minded people did not accept it. So he said, okay, I don't care, I'm going to start my own journal. And it's one of the best journals now. Is it Archives of Rational Mechanics? Who is that person? Truesdale. Okay, so this is the situation now we are in. So we will work with axiomatic set. Set theory, we will assume axiom of choice from now on. In all our further discussions, I don't think there is any analysis that is done without axiom of choice. In fact, there is a group of people who don't even believe these existence theorems. There is a group which still has not taken really very well. It started in the 50s and 60s, up to early 70s it was a little bit strong, but now it's called constructive analysis. Everything must be constructed. You can't say there exists a basis. You show me what that basis is. Exactly, precisely, concretely construct the basis. But that I think is a little flop because you can't get too far. See, in philosophical, logical, deductive reasoning and arguments, it is the argument which leads to the conclusion. It is not the physical appearance of the conclusion that is believed. Therefore, it is not the physical appearance of it, actually the logic that led to that is more important. So again, there are lots of funny things that are there, but you have to. Okay. Now I am going to perhaps almost finish most of the preliminaries that you keep appearing again and again whenever you are doing analysis. Axiom of choice is one important aspect which will come. But before next topic that I will choose is basically real numbers. Okay, that is where the real analysis starts. There also there is quite a few questions. But before that, I want to make one or two comments about this. What are known as ordinal numbers. We have seen what are cardinal numbers. I'll also look at what are known as ordinal numbers, just very briefly. So, just a few preliminaries to start with. Suppose I have two sets, A and B. Now I can think both of them are the same, essentially the same, if they are equivalent. Okay, if they are equivalent, that means there is a mapping from A to B which is 1, 1 and on 2. That is, that F is the coding of A as B. So B is essentially A, is being encoded through this isomorphism F. So we can think of both of them containing the same information. So we say A is equivalent to A. And with each set, we associate a symbol called the cardinality of A, and when these two happen, these two are equal. Now, suppose in addition to being sets, they also have a certain order in them. So suppose I have let me call it as now two orders. One is the B order, one is the A order. Now if I have a function from here to here, now there is a lot of coding to be done. The coding of the elements, also the order. Suppose it is such that the coded version also preserves the order. That is, F is 1, 1 on 2 from A to B, and A less than or A1 less than or equal to A2. When I put this, that means in this order, implies the coded version also maintain the order. So again, it's an encoding as a package. Not only the elements are encoded, the order is also. So in particular, so these are, we can think of this as a partial order set to partial order set. In particular, if I have a totally ordered set, F11 and on 2 from A to B, and A1 less than A2 implies FA1 FA2. Then we call it an order preserving isomorphism, just or order isomorphism. F is called an order isomorphism from to now, just like we associated a symbol with each set, we are going to associate a symbol with each totally ordered set. Okay? So, with each totally ordered set, we associate a symbol with totally ordered set E. We call it order A. We call it the order type A. Order type, call it. There we call it cardinal number. We call it the order type. Okay. Just like we say that if two sets are equivalent, we have the same symbol is given to them. If two sets have this order isomorphism, then we associate the same order type. Of course, if there exists an order isomorphism, if there exists such a F, we say this fellow is congruent to or isomorphic to order isomorphic. This symbol we use instead of another symbol of equivalence. Okay, and if A is isomorphic, order isomorphic to BB, we associate the same symbol. Same order type. That is, order type A will be equal to order type. Now, in particular, if you do it for if A and B are also well-ordered sets, then the order type corresponding to A is called an ordinal number. If lost that statement I write. If somebody wanted to A is a well-ordered set, then it is also a Zetto set, and therefore odd type A is defined. Such an ordered type is called an ordinal number. See, what we are saying is, when we look at numbers, first we looked at only the size. If anything is the same size as n, we called it cardinality alephna. However, the numbers are not just numbers. They have certain structure within them, namely certain order. The normal thing we think of when the integers, first order we think of is less than or equal to. So it is not only that the other fellow we identify can be coded, but the order should be maintained so that fellow can be thought of as another incarnation of this particular same number. So the order reincarnation is also important. So the two types of orders we can think of are the total order and the well order. So whenever you have, for example, if you look at the set 1, 2 up to n. So what is if we have an empty set, we define the order type to be 0. If you have any finite set with the finite set of integers, what is the usual order? That is less than or equal to. We define the same n as its order type. And if you have the rational numbers, we introduce the symbol eta, and if you have the natural numbers, we introduce the symbol omega. This is different from a left nut in the sense that this order is also taken into account. Not if somebody must be equivalent to n as a set, not only as a set, but he must also have an order, and that orders must also be preserved under this isomorphic map. If you look at this, this is an ordinal number because this is a well-ordered set. This is an ordinal number, but this is not an ordinal number. This is only an ordered type because Q is not a well-ordered set in the usual thing. So therefore, only well-ordered sets will generate the ordinal numbers. So in other words, you want to put fellows in a properly organized manner. Every non-empty set must have a first element. So essentially, we can now carry out the same type, almost similar type of arithmetic that we did for cardinal numbers. Every time we take a representative set there and then define the order, etc., etc. So here also we have to take a representative set and work and then show that the work we did is independent of the representative set we choose and so on and so forth. In particular, we can say that one ordinal number is smaller than another ordinal number. Law of trichotomy, similar things we can start looking at. I will just for the first 15 minutes of the next class, first 15-20 minutes, I'll just quickly summarize some of these properties of these ordinal numbers, and then we'll take on the real numbers. Right. So, if this were in, I am done. I have already constructed an upper. This will be an upper bound if for C, if x belongs